morning, welcome back. So we will come back to the axiom based discrete event simulation programs. So we saw two examples yesterday, the MM1Q system as well as the Aloha protocol, right. So those are two basic examples that we saw. With MM1 we saw the infinite buffer and how we use the resource object that is available in the axiom, and with Aloha we showed how we can actually use our own buffers to add packets, to delete packets, and then process the packets based on that those buffers. So now we look at this sort of example we have been looking at most of the course, where there is a job or a set of jobs that are sequencing through the CPU and then taking or requesting service from one or more disks and then coming back to the CPU. So your typical process in execution, right, a Unix process or any system process for that matter, right, runs on the CPU, requests some sort of input output, then repeats this loop endlessly until it actually finishes the system, right. And in this example today we look at a closed queuing system where there is a fixed number of jobs in circulation, and we have seen this before, right, time sharing systems and so on. We want to look at the throughput of the system in terms of how the number of jobs is fixed, say 10 or so, and then based on that, as these jobs sequence through the CPU and the disk, what is the effective throughput of the system, in the sense how many jobs per second can be completed. So we have looked at techniques, mean value analysis and related systems, right, to understand how this can be measured, all these different performance metrics. But whereas we need a way to compare the results that MBA or other techniques provide us, and simulation is a good way of validating the results that we get from the theoretical analysis. Okay. So in this example we have 9 processes that are 9 jobs as per the other terminology, which is called as token, that we see this process token, right. So this is 9 processes that are running in the system, and there is a single CPU that is time shared between these 4 processes or 9 processes, sorry, and then there is a set of disks. There are 4 disks in the system, right, which are shared among these 4 processes or 9 processes. So the processes can request the CPU, then one of these 4 disks, and then repeat this forever. That is the basic. So it is a closed queuing network that you have seen before. The jobs are of 2 types. This is only for just to show how we can actually make some things more flexible and more detailed in the simulation, right. So we can say there are 2 types of jobs, one which have 10 units of time of CPU execution, the other is 5 units of CPU execution. So there is the 2 classes of jobs that we have in the system, and the time that you request the disk, right, the amount of the average service time on each disk is defined to be 30 units, right, 30 time units. So that is our basic system that we have here, and now let us look at how we create a set of processes that are needed to get the simulation going, so, right. So if you look at user main, so there we will create first the set of processes and the corresponding set of resources that these processes are going to share. Okay. So this is the first loop. So there are 9 processes. So we create 9 processes, one for which with the corresponding ID. We use the activity set arg to let each process know what its ID is, because that is needed later on in time. Okay, and then we schedule this process to start right away. So there are 9 parallel processes running in the system. Each is going to execute. This token P is the function that is going to be executed by each of those 9 processes. So that is now established. So we have now created 9 parallel processes for execution. Now we use this new resource, the resource object that is provided by axiom, to create the CPU, which is again simple, because we know that you simply have to request the CPU, and if the CPU is busy, then you simply have to wait for the CPU to become free again. Okay. So therefore there is only one CPU, and this is the first come first served with priorities. This is one of the different scheduling algorithms, that is disciplines, that is by default available in axiom. Okay, so we have now created the CPU in the second step. Then we go ahead and create the disk. The disk is a simple first come first served disk. There is nothing special about it. There are 4 disks, and each disk has a corresponding resource that is allocated for that. Okay, and now there are 2 types of statistics records, one for the short jobs and one for the long jobs. That is all, right. So that is why we have delay 0 and delay 1. So all the short CPU processes will go and update this short statistic record, short the CPU stat, and the other one will update the other statistic record. Okay. We also measure the CPU utilization, as that is why we say collect statistics. If you do not do that, the system will not collect statistics, so we need to invoke this. We also collect statistics in terms of utilization for the 4 disks in the system. So that is our basic system done. Then we have this random init, and then the notion of select stream is in many simulators provided with the default set of random number streams. Okay, usually random numbers, the way it works is you have a starting number, starting seed, and then after that it is deterministic. All the subsequent random numbers from the same seed are going to follow the same pattern. It is usually some sort of mod operation, right, and then you will have a repeated sequence. So after a long time the sequence will repeat for any given stream, and because we want to have some predictability in the output, rather than use some arbitrary random number like time or some other entropy of the system, we try to have a set of say 16 random number streams, and we know that, but we want to have at least 16 different combinations. So what we will normally do is run the same simulation for 10 or more different random streams, and then look at the means and the confidence intervals based on that, right. So here select stream simply means select the 5th random stream. It does not matter what that stream is, we just want to use a particular random stream. And there is again one more statistics pointer which I am going to skip for now, right. So then we have this driver auto terminate function, which is the one that we talked about last class, where you run up to 1 million time units if necessary. If convergence takes place based on the delay, then you simply stop the system from simulation at that point in time. So once driver auto terminate finishes, automatically we know that this simulation is complete. Then we report all the statistics for the delay 0, delay 1, the CPU utilization, and for the disk utilization. So this is our performance metric analysis. So this is the basic system now. The 4 disks and the CPU are in place, and the 9 processes have started execution, right. So now we need to go and create the code for the token P, the function that is going to be executed by each CPU process, right, job in execution. And so this process, again, as we said before, is going to be a endless, right, it's a endless while loop, or a do while loop in this case, that simply executes forever, and whenever the system simulation terminates, automatically this will just get terminated, right. So anyway, so this again is to get the correspondence for every process. You need to find out which, when this token P is executing, you need to know what is the corresponding process number, and that is what is obtained from this activity get arg, and then you set the priority based on the token number. Okay, and then if you look at the actual code, it is simply using the CPU for some exponential amount of service time, right, and again here if you look at it, right, if the token number is greater than 5, then it will have there is an array here, right, your CPU service time is an array of 2 elements. So if your token number is greater than 5, then you will have mean service time of 5 units. If it is less than 5, mean service time is 10 units, that is all. Okay. So this is how you request the CPU. CPU is busy, you have to wait until that CPU gets allocated. So then, so the resource use is slightly different from what we saw before, right. Previously we had a process which used activity scheduled resource. Here this simply says use the resource. So the resource use will automatically queue the process. When the process is completed by the CPU, then it goes on to the next statement. So this is actually a blocked statement, so you have to understand that, right. This will block this particular process until it gets selected by the CPU. So there is a lot of fine detail which is conveniently hidden by Axiom, but for us logically it is simply use the CPU, use the disk, right. So here again I randomly choose one of those 4 disks, and this is the service time is based on this Erlang distribution, right, which is something again predefined in Axiom. So we can look at that later on if necessary, but instead of exponential service time, it is now some Erlang service time based on these 2 parameters. This is the mean, and if you look at Erlang, there is also shape parameter, right. This is A, B are the 2 parameters. So mean is 1, and the shape parameter tells you what will be the service time. So it's another random variable defined by this Erlang distribution. Okay. So then resource use for the CPU, resource use for the disk, and then finally when we are done, so I have used the CPU, I have used the disk, and then I simply update the delay statistics record, right, based on the time that so before the process, remember the process executes forever. So in the current run, right, for the current CPU disk quantum, I get the time before that particular run started. When the run finishes, this is the amount of time that I ran on the disk and the CPU, and then technically if you look at it, this is probably some other job in the system, but just the same job. In our simulation we are conveniently assuming that it is the same job. In theory it could be some other job, right. It is like one job finishes and some other job replaces that. Only difference is these 2 jobs have the same parameters in terms of CPU execution time and disk service time, therefore it is just, right, conveniently replaced, but we consider that as a closed queuing system, right. This is how we do multi-programming, right. So we want to look at, if I run 10 jobs in the system, what is the effective throughput of the system. If I run 5 jobs in the system, what is the throughput of the system, and you want to plot this graph in terms of number of jobs in the system versus the effective throughput of the system, right. As the number of jobs is very small, throughput will be small, but when you increase the number of jobs to a very large number, then what will happen is queuing will happen, right, lots of queuing will build up, which means your throughput will essentially come down. So you want to find out the optimal system operating point in terms of the number of jobs that can be active in the system. That is your degree of multi-programming, as far as if you will see that in OS textbooks. Okay, so that's all. Okay, and so this is the basic definition for the system. So all the analysis we did MBA, right, we can conveniently compare. In MBA we didn't have this notion of two different service times. We assume that all the service times are the same on the CPU. Here I have this slide modification in terms of two different service times depending on the process itself. Okay. So now let us see if I can actually get this to compile. Well, not compile, we will simply run it. There is a compiled code that is available. So CPU disk, we do not have to specify any parameters, right, because everything is predefined. This is the number of processors, service time, all that is predefined, and this is finally what we get in terms of the system output, right. So what we let me just go here. Okay, so this is the we simply output, this is a histogram, right, of the different delays. So this is something that Axiom also computes for you. It says that between 0 and 40, right, 11% of the process delays of the for each process was between 0 and 40 time units, and 27% was in this time units, and so on, right. So this gives you the distribution, right, in terms of the number of samples that fall within these different histogram bins. So that is something little more detailed than simply the mean value, right. So mean value we know it is simply 106 units of time, but the distribution is given by this particular system. So there are some jobs that take up to 360 units of time. So the mean is only representative, right. So you find that there are a very small number of actually they take 360, so it is a fairly long tail, and but about 25% of the jobs take, right, somewhere between 80 and 40 units of time, and so on. Okay, so that is the histogram. For this is for the longer jobs with average service time of 10 units on the CPU, so 106 units of time. For the shorter jobs it is 75 units of time is the mean, that is what we observe here, right. And look at the number of samples and sampling interval, and if you look at the max value, in the worst case it is 470, and in some cases it is pretty quick because this is exponentially distributed service time, right. So we get that as 0.76 is the minimum and maximum is about 470 or so. Okay. Then we have utilization of the CPU. So this CPU utilization is 0.765. If you remember MBA calculation, that is what we try to find out, right, utilization of the CPU. So that is 0.76, and disk utilization, this is the first disk, right, disk number 1, disk number 2, and so on. So this is the disk utilizations are about 0.72, 0.72, 0.73 and 0.72. So they are all roughly the same because we are uniformly randomly selecting any one of those 4 disks for the system operation. Okay. So that is essentially what we have. This is the way you can actually compare your MBA results, right, and then validate that with the help of this particular simulation. So this can be expanded. Now we can write more complicated programs, right, with the help of this with the basic mechanism. So all the basic queues are available. So we can now construct larger and larger queuing networks. We only saw a single queue before. Now this is a network of queues, right. So I can actually feed packets from one queue to the other, and so on. All right. So that is the sort of concluding part of this axiom that I had wanted to talk about. So questions on this, on the code or on the analysis? No questions? Everything is clear? Okay. Okay, so now we have seen, right, 3 sample programs, and so if you are taking this class or going through these lectures on NPTEL, then we also need to practice some of writing our own programs, right. It is not enough just to look at code and look at samples, and so when you might be wanting to write your own simulation program for whatever purpose, whatever be your application, you can write your own, but just to get you started, there are a couple of other programming assignments that we have developed. We will take a quick look at those. Okay, so we saw the MM1 cube sample program, so we wanted to generalize this, so you can take this as an attempt, right. This is part of the assignment that was given for the CS621 course, but you can essentially try to generalize this to a MGM/BQ, where the service time, right, can be either exponential or it can be specified by some sort of PMF, right. The service time can be actually given to you as an input, rather than saying the service time is exponential. We can actually define the probability distribution, the probability mass function for the service times, and then based on that you should be able to randomly generate for every packet that arrives, every customer that arrives, you will determine the service time based on this distribution. Okay. So for example, if you look at this system here, we are saying that there are 4 different service times possible. So with the probability 0.3, which is the second parameter here, the service time will be 0.2 units. With probability 0.35, the service time is 0.4 units, 0.6 service time units, and so on, right. So these are the all possible combinations, and if you look at it, all the probability should add up to 1, right. So this is your PMF for the particular system. So now you will have to generate, which is easy to do with the help of the uniform random distribution. All that is sort of left unspecified, but we can convert this MMN program into a very generic MGM/B program. So to get in the B, you will have to implement your own server to bring in the finite buffers, as we talked about. Whether Yaxim provides finite buffers or not is not clear, but we can very easily provide our own finite buffer capabilities, and also multiple servers, everything we can handle by writing these things ourselves. Okay. And in terms of measurements, the metrics that we want to measure from the system, average packet delay, this is something that we can very easily measure, we have seen examples for that, and also variance of the packet delay, right. So now that you have all the samples, you can easily compute the variance. We can, if you look at the results from Raj Jain, right, variance is available for MM1 results available, right, but if you want to do MGM/B, then variance is not going to be easily available as a closed formula. So you have to closed form formula. So you have to resort to something like simulation to actually get the service variance time in this particular packet delay variance in this particular environment. Okay. We can also measure the average length of busy period for the different servers, and also packet drop probability, because when the buffer size is infinite, there is no packet drop. When the buffer size is not infinite, then arriving packets will find the buffer full, packets can get dropped, and those things again, those things you can measure easily with the help of simulation. And likewise, if you look at our MM1B, there are results for the closed form results for the blocking probability, right, that is easily available, but for a more generic system it is not easily available. So that is why we would need to resort to simulation, as we have seen in this particular case. So that is the basic setup, and then there are, right, all sorts of variations in terms of different number of servers, different arrival rates for the system, as well as different values for the buffer size. So these are all combinations that one can look at. Okay. And there is also a slotted Aloha model that is available, that was discussed in class in an earlier lecture, and what we can do is we can also try to at part of that model, what we had was a large transition matrix. So we defined that as a Markov chain, where there are different states for the system in terms of the number of packets that is being transmitted, number of packets in back off, and so on. So we had a fairly complex state transition probability matrix. And so what do you do with the state transition probability matrix? This is a way of, you can actually encode that and codify that in MATLAB or Mathematica or Scilab or any other package, right, and then you can solve, solve for that and get the steady state probabilities based on the transition matrix. That is also a very straightforward exercise. And so once we do that, so once we define the number of users in the system, the back-off transmission probability, the new packet transmission probability, right, you can simply generate the transition matrix based on those values, and then we can, if you remember, this is from the Gallagher's textbook that we were trying to, that we had discussed earlier in class. Okay. So this is a way of trying to take a mathematical model and actually getting numerical results for that, right. Sometimes numerical results have to be achieved by these means. And anyway, and as long as your matrix size is small, you should be able to get the results in reasonable amount of time, otherwise you have to resort to some sort of approximation methods to get these. So this is another experiment that you could try in order to, right, validate some of what you have seen in terms of the theoretical model. So we have looked at the extension from MM1 to MGM/B, as well as that theoretical slotted Aloha model that we saw can also be verified numerically with the help of implementing those equations in MATLAB. So that is one exercise that you can try out, and there are a lot of other optional exercises also, which we have listed here. I will talk about, right, one or two of them. In class we had seen that the departure process from MM1Q is also Poisson, right. The arrival process is Poisson, that is an input with rate lambda, and we proved in class the departure is also Poisson with rate lambda. Now how do you verify that with the help of simulation, right. So what you have to do is you will have to record the departure process. So every time a process or a customer leaves the system, you would note the time, which we only right now record the delays. We should now also record the instance of time when those customers are leaving the system, right. So you keep track of the inter departure times. So you have a set of sample of inter-departure times. Now we will have to map that and find out whether that actually follows a exponential process, right. If the inter-departure time is exponential, then we know that the departure process is also exponential. So if you look at Raj Jain's book, there is a way of looking at the quantile distributions and showing whether the sample values from a given system is matching an exponential distribution or not. So that is an exercise that is fairly easy to figure out, okay. And then we also had seen in class that if I concatenate or create a tandem of two queues, both MM1, where the first MM1 queue finishes service and feeds that to the second MM1 queue, we saw that the delay in the system is the sum of the delay spent in each of those two queues. That is also something that was covered in class. Now that is very easy to verify that with the simulation, right. So that was, we said that if there are two queues with arrival rate lambda and mu1 mu2 as the corresponding departure rates, then the total delay in the system is 1 by mu1 minus lambda plus 1 by mu2 minus lambda, okay. So you can verify that. So we can verify that also with the help of creating a tandem of queues where packets arrive to one queue. When a packet departs the first queue, it simply gets joined to the next queue in the system. So that is a simple tandem of queues. It is a very simple example of a queuing network. It is not really a network, but anyway there are more than one node, therefore it technically becomes a network. So there are lots of other variations also that one can try out, right. So only when you try these things will you get comfortable with the action and then try to use those in your corresponding experiments or studies or projects that you are planning to use later on, okay. So that is one of the programming assignments that you could try out. Now there is another one which we will discuss in about 5 minutes and then we will stop at that. So that was an open queuing right, an open queuing system primarily. Now we have also defined another program for creating a closed queuing network, right. Any of our we have seen a lot of examples in class like the CPU disk problem we saw earlier today. We can create a more complex network, right, and we can again create a set of queues and connect those queues together where the packets from one queue can reach some other queue based on some probability distribution and so on, and that is what this assignment is all about. So you will create a set of queues and simulate the transition of packets between these queues. When a packet finishes service in one queue, it automatically goes to one of the other queues in the system, and then this is again a closed queuing system. So we have a number of jobs, right, n jobs in the system is predefined, and then we want to find out the throughput of the system, right. So we have seen x of n, r of n in class. X of n is the throughput and r of n is the corresponding response time. So we can actually implement this as well as compare, right, these results with the MVA algorithm. So MVA algorithm is defined, it is a very straightforward algorithm, it is a simply iterative algorithm, right, and where you start from n equals 1, 2, 3 and so on up to n equals 10, whatever be the number of values that you have specified. So you can compare your MVA algorithm with your with this particular algorithm, and you can basically construct any network that you want to. So the specifications for the network creation are given in this example here, right, where you specify the number of queues and which is going to be the in queue, which is going to be the out queue, because in the case of closed queuing system, right, something has to be marked as the in and the out queue to find out the out in link, and then we have past that, right. So we need to specify for each queue in the system, right, the corresponding parameters in terms of the index for that, the average service time, right, the number of servers at the queue and things like that. So we can actually simulate not just single server at each queue, you can simulate multiple servers at each queue and then say, right, and then look at the system performance based on that, okay. So this is also a little bit more complex, but it is doable, and this combined with implementing MVA will give you a better understanding of the performance that you can get with these systems, right. Otherwise it is all theory on paper and you won't really get the same, I guess, value add or understanding that you will get from implementing these systems, so that you can use them for later of your own exercises later on, okay. So that was the basic part about the discrete event simulation that I wanted to talk about. So any questions? No questions? Okay. So we will stop here for this part, and then we are going to continue next on stochastic Petri nets, which are Petri nets in general and followed by stochastic Petri nets,